Welcome to the screencast for 3.1 part 1. So this chapter is all about exponential and logarithmic functions. Ideally this will only take about 10 minutes, so we'll get started. So exponential functions are power functions, right, where the base is a constant and the exponent is the variable. So for instance, 2 to the x, this is a power function. Maybe like pi to the x, you have a constant as your base and your exponent is going to be a variable. So all exponential functions have asymptotes and they increase rapidly. So here are a couple of examples. An exponential function with base b has the form f of x equals a times b to the x power. A cannot be 0, otherwise the whole thing would be 0, right? Because if that's 0, everything would equal 0. B has to be positive, and it can't equal 1, because anything to the first power is itself, and then we would just have a number constant. Okay, so here's some examples, right? We have a constant, and then we have an exponent that's a variable. We have a constant, 1/3, and our exponent's a variable. We have a constant, and then our exponent is going to be a variable. So remember, we said b has to be positive, and it can't be 1, right? Because if we have a negative number to an exponent, that means we would be multiplying, and it would keep switching over the sides of the graph, right? -2 to the squared is 4. But if I take -2 and cube it, it's going to be -8. So it would get really, really jaggedy. It would not be ideal. Okay, so although our exponent is negative, that's fine. Another way to write it would just be 1/7 to the x power. So nothing bad. A couple non-examples. Notice we don't have a constant as our base. This one, we don't have a variable as the exponent, and then our base can't be 1. Here are more examples of exponential functions. Notice all of these have a number as the base, and we have a exponent that is a variable. So this has a variable, x minus 1, all that does is shift it left and right. Properties of exponential functions. So we can have exponential growth and exponential decay. So the growth, for an example, is like bacteria growing rapidly. We're going to have a lot of different examples later in the lesson about things that grow. Weirdly, I was on Reddit yesterday, and this virus that's in China is growing exponentially. So that's actually a real-world example. So the people that were modeling that used exponential growth in a variety of factors. So notice that all exponential functions have the domain all real numbers. Right, so their domain is always all real numbers, so you can plug in any x value and you'll get a y out, but the range is only 0 to infinity. And notice that 0 is not square bracket. So what this means is we have an asymptote that is the x-axis. There's an asymptote here, and it will never go below this asymptote. That also means something like e to the x can never equal 0, because there's no exponent here that would make it go to 0. Because any number to the 0 power is 1. I could pick a really, really, really negative number. Still, e to the -100 is just 1/e to the 100. That's still a number that's larger than 0. So this exponential function can never cross the x-axis, and it can never touch the x-axis. So the range, we don't include 0. Domain's always all real numbers. The end behavior, as we go left side, it's getting closer and closer to 0. We'll never equal 0, but it'll get close. And on the right side, we're approaching infinity because it just goes up forever. This is in contrast to exponential decay, right? So this is bacteria dying quickly. Right? It's really killing off. So this is like when I was sick and taking antibiotics, the number of bacteria that I had in my system really died. So notice that the domain is still all real numbers. The range is still 0 to infinity, right? Our asymptote is still this x-axis. We're all above it. But the difference is the end behavior flipped. Okay, and it's continuous. So a function is classified as exponential growth if our base is larger than 1, and decay if our base is between 0 and 1. Because remember, our base can't be negative. So classify as exponential growth or decay. So you can pause the video, try it yourself, and we will get going. So this base is 2, so we know it's going to be growth. Here, this base is 0.5. 0.5 is between 0 and 1, so we know it will be decay. I have a base that's between 0 and 1, so this is going to be decay. And then, ooh, this one's weird. If we can just rewrite it. Instead of having 1/4 to the negative x, I can flip it to be 4/1 to the x. I get rid of the negative by moving things on the other side of the fraction. So this is literally just going to be 4 to the x, which is going to be growth. Perfect. So now we want to graph and analyze each function. Describe the asymptote, range, y-intercept, and behavior continuity. Okay, so 2 to the x power. Our asymptote is going to be at y equals 0 because I'm not moving it up or down. If I added 1 here, my whole graph would shift up by 1, including my asymptote. So our asymptote is the x-axis. So the line would be y equals 0. The y-intercept. So remember, this is where x is equal to 0. So if I plug in 0 for x, I have 2 to the 0, which is just 1. So our intercept is at 0, 1. Oops. Okay, so we can go ahead and draw this. Let me put my, y equals 0. It's kind of hard to see, but it's on the x-axis. It will be easier to see once we have vertical translations. Y-intercept 0, 1. Okay, and I gave you some values already. So we want to plug in and find a couple points. That way we can draw our graph. So -1. So let me put -1 in for x. Well, 2 to the -1 is the same thing as 1/2. So I have a f of x that's a half. So -1, half. Ooh, I should use a different color. Let me use blue. Here, here. All right, 2 to the 0, we already know is 1. 2 to the first is 2. 2 squared is 4. So 1, 2, 2, 4. I could even do like 2 cubed, right? 2 cubed is 8, so cube 8. So it's going to be this nice exponentially rapidly growing problem. As we go to the right and as we go to the left, it gets closer and closer to 0. So look at the graph, see if you can fill in the domain and range. No surprise, the domain is -infinity to infinity. It's all real numbers, but our range is 0 to infinity because we don't go below the x-axis. The end behavior, as we go to the left, we're approaching 0. As we go to the right, we're approaching infinity. And then where are we continuous, right? Do we have any holes, discontinuities? Nope. So we're continuous for all real numbers. Okay, now let's try a different one. I have 3 to the -x. So this can be written as 1/3 to the x, or you could write it as 1/3 to the x power. So this is going to be decay because our base is between 0 and 1. We're still going to have the same asymptote because I'm not shifting my exponential function up or down. Our y-intercept is still going to be 0, 1. Because if you think about it, 1/3 to the 0 power is still 1. All right, so we're all good. And then let's plug in some of these values. So 3 to the -x, 3 to the negative of -2. So this is going to be 3 to the 2, which is going to be 9. 3 to the negative of -1, that's 3 to the first power, which is 3. 3 to the negative of 0, well, that's just 3 to the 0, which is 1. 3 to the -1 is 1/3. Okay, put everything on our graph. So we have our asymptote, y equals 0. This is, hopefully you can see these. Hopefully you can see the line. Okay, we have a y-intercept 0, 1. Let's see, a -2, we're at 9. -1, we're at 3. And 1, we're at 1/3. Okay, so connect them, and we are rapidly decaying. Oops. As we come to the left, we are going up to infinity, and as we go to the right, we're getting closer and closer to our x-axis, but we're not crossing it. Very important, we do not cross this. So domain is going to be all round numbers again. Our range is still 0 to infinity. Notice it's always smallest on left, bigger on right. Right? It's always going to be written this way. You never write it as infinity to 0. You always go smallest to biggest, left to right. All right, left end behavior, we're going to infinity, and right end behavior, we're going to 0. But we're still continuous for all real numbers, right? -infinity to infinity. So the same techniques of transformations can also apply to exponential functions. Remember, vertical translation will shift the asymptote of the function as well. So this is what I tried saying before. 3 different transformations are applied to the graph f of x equals 2 to the x below. So I want you to pause the video and look at what is different. So here you can see we have the x plus 1 versus x. If I take a certain point, everything is being shifted left by 1, left by 1, left by 1, left by 1. Because remember, if we had something like absolute value of x plus 1, or if we have, x plus 1 squared, or square root x plus 1, all of these are horizontal transformations. All right, they all are horizontal translations left. So this is where we have horizontal movement. The x plus 1 is movement to the left. Now, this is a little different than the middle one. So if you look at what's different, we have a negative versus a positive. So we have a reflection over the y-axis, right? If I take this guy and flip it over the y-axis, it turns into the other graph. Okay, so I'll highlight. This is, so remember, 2 to the x is growth, and 2 to the negative x is going to be decay. Because if I rewrite it, it's the same thing as 1 over 2 to the x. Okay, so this is just reflection over the y-axis. And lastly, we can have reflection over the x-axis, right? All we need is a negative number in front of our base. All right, so when we have y equals a b to the x, right, this a, the coefficient, if it's negative, all that does is it flips it across the x-axis. All right, so that was, all of this was talking about exponential functions. So really, like, what's the difference between growth and decay? So now here's the most important exponential. It's literally called the exponential function. Right? If we have a natural base. In most real-world applications involving exponential functions involve an irrational number called e. Right? So this is a number, e. It's called the natural base. It's literally defined as this. So you already know what a limit is. This is going to be the end behavior, right? What's happening at the end of this function? So if you think about it, I plug in infinity for x. See, 1 over infinity, well, that goes to close to be 0, but this goes to infinity as well. So what's going to win out? Right? As we get closer and closer to infinity, the number inside the parentheses gets smaller and smaller, close to 1, but we're multiplying by infinity, or multiplying infinity number of times. So any number larger than 1 times itself multiple times, right? Because 1 times 1 is literally 1.21. It's just going to keep growing way larger. So it's this fight, like who's going to win out in the end? So the answer to that, literally, the limit of this function is e. This is the number it actually approaches. Because roughly this graph looks like that. So more or less the limit as we go to infinity, we have a horizontal asymptote and it's literally at 2.72, aka e. That is the end behavior. Cool. So as x goes to infinity, the value of the expression comes exceedingly close to 2.7183. Hence, the accepted value of the irrational number is 2.71 blah blah blah. All right, so 2.72. About. All right, so this is the last page we're going to do for the screencast. Hopefully all of this is mostly review. So example 3, graph and analyze the function, describe the asymptotes, domain, range, y-intercept, blah blah blah. So first, this is still just a number to an exponent, right? And our exponent's a variable. So since this is larger than 1, we know it's going to be growth. We still have the same asymptote at y equals 0. We haven't shifted up or down. If I put e to the 0, well, anything to the 0 is just 1. So I just am at 0, 1. Plug in a couple of these values. E to the negative 1 is literally 1 over 2.72. So it's about 0.37. If I put e to the 0, that's just going to be 1. E to the first power is about 2.72. E squared, if you take 2.72 times 2.72, it's about 7.4. Okay, so this, of course, we're going to have to do a little bit of estimations on our graph, but that's fine. All right. Let's go and graph this. I have a point at 0, 1. Point at -1, 0.37. Okay, so it's a little less than half. And at 1, I go up to 2 and maybe 3/4 about. And then let's see, 2, 7.4. Let's see, it's about right here. Something like that. So all of our growth roughly looks the same, right? All of our growth equations. Perfect. Don't touch. Okay, so don't touch and don't cross the x-axis, but that's roughly what it looks like. It's just this like loop going up. The domain, well, it's still all real numbers. Our range is still 0 to infinity, right? Because we haven't shifted up or down at all, right? All of these are just the most basic functions. Our left-hand behavior, we're approaching 0 as we go left. As we go right, we're approaching infinity, and then we'll be continuous on all real numbers. Cool. So hopefully this was helpful. Tomorrow in class, we will hit this a little harder.